Assalamualaikum warahmatullahi wabarakatuh. My name Muhammad Iswandi bin Ishaq. Today I will present my assignment entitled Titanium Alloy. My presentation will cover the introduction, the titanium alloy, meaning the metallurgy of the alloy, the processing method, the heat treatment, strengthening mechanism, failure mechanism, sustainability, and finally the conclusion. Titanium alloy, in terms of metallurgy of titanium alloys can be categorized into few categories. Number one is pure titanium. Secondly is alpha titanium alloys. Number three, beta titanium alloys. Then alpha beta titanium alloys. And finally, near alpha titanium alloys. In terms of titanium has low thermal conductivity and it has moderate strength, low elastic modulus, and high corrosion resistance. It has two crystal structures. Depends on range of properties. There is SCP and BCC. Unalloyed titanium is favored for its high corrosion resistance, while the impurities will increase the strength but will reduce the resistance. Applications always used in chemical and petrochemical industries such as heat exchangers, pipings, reactors, pumps, and valves. For alpha titanium, the most commonly used all alpha alloys always contains 5% of aluminium and 2.5% of tin, which will enhance HCP alpha structure. The high temperature will cause the alloy to anneal into beta region, but with rapid cooling will result in good fatigue resistance. Neutral elements like tin and zirconium will strengthen the alpha phase with minimal impact on transformation temperature. Example of these alpha alloys are titanium 6 aluminum 4 vanadium and also titanium 6 aluminum 6 vanadium and 2 stannum, which are widely used in industries such as for aerospace industries, military, medical, and also sports. For beta titanium, beta alloys are a type of titanium alloy with a BCC beta phase structure. The beta phase is less stable than the HCP alpha phase at room temperature, and it allows for more atom vibration due to its less dense structure. Beta alloys contain stabilizing elements and alloying elements that result in a strengthened metastable beta structure after quick cooling, but tend to be less ductile and tough as compared to alpha alloys and can be harder to work with. Example of these alloys are titanium 15 vanadium, 3 chromium, 3 aluminium, and also titanium 13 vanadium, 11 chromium, and 3 aluminium, which always used in high strength fasteners, beams, and also for aircraft components. For alpha beta titanium, the ideal balance of alpha and beta stabilizers can result in a mixture of both phases at room temperatures. One example of this is the widely used titanium alloy, titanium 6 and aluminium 4 vanadium. The microstructure and properties of these alloys can be controlled through heat treatment as they possess two phases. Lastly, for near alpha titanium, the near alpha alloys are a type of titanium alloys with a mixture of alpha and beta phase structures, offering a balance of the high ductility and toughness of alpha alloys, strength of beta alloys, and good corrosion resistance with low density. This kind of alloys always used in aerospace, military, and industrial application. An example of this alloy include titanium 6 aluminum 2 stannum 4 zirconium and 2 molybdenum, and also titanium 5 aluminum 2.5 stannum 1 zirconium and 0.7 moly and 0.3 silicon. Then we go further uh, about processing. How to process the titanium. The process of titanium involves several steps, including reducing the titanium ore to sponge, then melt the sponge to form ingots, converting the ingots into mill products, and fabricating finished products through various methods like forging, extrusion, hot or cold forming, machining, chemical milling, and joining. The microstructure and characteristic of titanium alloys can be altered by these processes. So, controlling the microstructure is important. The high cost of titanium and its alloy is due to the complex extraction process, challenging melting process, and also difficulties in manufacturing and machining. So, to reduce costs, near net shape techniques like casting, isothermal forging, and powder metallurgy have been developed, but conventional machining or traditional machining still dominates the production of titanium products. In terms of heat treatment, basically, generally, the alloys of titanium can be heat treated by annealing, quenching, precipitation hardening, edge hardening, and also cryogenic treatment. So, for strengthening of alloy, titanium alloy, the process we can use whether co-rolling or addition of carbon in the alloy, or through the severe plastic deformation, or we can choose to use low-cost alloying elements. In terms of failure mechanism in titanium alloys are generally related to the interaction between the material's mechanical properties, manufacturing process, and environmental conditions. So one of the failure mechanism that very common in titanium alloy is fatigue failure. For sustainability of titanium alloys production is a concern for sustainability due to high energy consumption, resource usage, and waste generation, leading to environmental degradation, including soil and water contamination and habitat loss. Finally, as a conclusion, titanium alloys are widely used despite the challenges and issues encountered in their processing, including high costs, difficulties in fabrication, and environmental concerns. However, by understanding the properties, processing methods, and failure mechanism of titanium alloys can help to improve their performance and reliability. Ongoing efforts towards sustainability in the production and use of titanium alloys will ensure their continued use in various industries. That's all from me. Thank you very much.